Okay, dual simplex method last in fourth module. Today we are going to discuss integer programming. Okay, integer programming means if all the decision variables are restricted to integers in an LPP, then it is called integer linear programming. That means suppose we have an LPP and we have an extra condition, all the decision variables are integers. Okay, in LPP there is only one restriction, that is called non-negative restrictions, that is x1, x2, x3, etc. Our decision variables are positive. Okay, this is another thing, and sometimes in some applications the decision variables should be an integer. Okay, but for example, the number of objects are optimized in the number of, suppose we have to optimize number of sensors, then that should be an integer. Okay, so that depends on context. But in situations, decision variables should be an integer. Okay, that is the context of mixed integer. That is the context of integer linear programming problem. Okay, next one, mixed integer linear programming problem. That means in some variables are integers, not all of them. Such situations are called mixed integer linear programming problem. So, decision variables integers. Okay. Then there are one more integer programming problem, that is called 0-1 integer programming problem. Okay, 0-1 integer programming problem is basically for yes or no type optimization type problems. Yes or no type means ചില സ്ഥാനം ഇപ്പോൾ എന്താ യെസ് ഓർ നോ ക്വസ്റ്റ്യൻസ്, ഇപ്പോൾ ഒരു റോബോട്ട് മൂവ് ചെയ്യാൻ വേണ്ടിയിട്ട് നമുക്ക് കുറേ സെൻസേഴ്സ്, സപ്പോസ് വി കൺസിഡർ ഷോപ്പിംഗ് കോംപ്ലക്സ്, ആൻഡ് അവിടെ ഒരു റോബോട്ട് ഇങ്ങനെ മൂവ് ചെയ്ത് എന്തെങ്കിലും പ്രോഡക്റ്റ്സ് എടുത്ത് കൊടുക്കാനോ എന്തെങ്കിലുമൊക്കെ എന്ന് വിചാരിക്കുക, അല്ലെങ്കിൽ ഹോട്ടലിൽ സെർവ് ചെയ്യാനാണെന്ന് വിചാരിക്കുക. അപ്പോൾ ഉറപ്പായിട്ടും കുറേ സെൻസേഴ്സ് വെക്കേണ്ടി വരും ഈ റോബോട്ടിനെ ഇതിൻ്റെ പൊസിഷനൊക്കെ ഐഡൻറ്റിഫൈ ചെയ്തൊക്കെ മൂവ് ചെയ്യണമെങ്കിൽ ചിലപ്പോൾ. അപ്പോൾ നമ്മൾ കുറേ പൊസിഷൻസ് ഐഡൻറ്റിഫൈ ചെയ്തിട്ട് അവിടെ സെൻസർ വേണോ വേണ്ടേ, യെസ് ഓർ നോ. യെസ് ഓർ നോ ടൈപ്പ് ക്വസ്റ്റ്യൻസ് വരുമ്പോൾ അവിടെ നമ്മൾ അവിടെ അങ്ങനെ ഒപ്റ്റിമൈസേഷൻ വരേണ്ട സമയത്ത് വി യൂസ് 0-1 ഇൻറ്റിജർ പ്രോഗ്രാമിംഗ് പ്രോബ്ലം. ഓക്കെ, അതുപോലെ ഇപ്പോൾ ഒരു ഷിപ്പിൽ നമ്മൾ കണ്ടെയ്നേഴ്സ് ലോഡ് ചെയ്യുകയാണ്. അപ്പോൾ ഡിഫറെൻറ്റ് ടൈപ്പ് ഓഫ് കണ്ടെയ്നേഴ്സ് ഉണ്ടാവും, പല വെയിറ്റ് ഉള്ളത്, പല ഡയമെൻഷൻ ഉള്ളതൊക്കെ ഉണ്ടാവും. ഓക്കെ, അപ്പോൾ ഏതെല്ലാം കണ്ടെയ്നേഴ്സ് ആ പർട്ടിക്കുലർ ഷിപ്പിലോട്ട് ലോഡ് ചെയ്യണം ഫോർ ഒപ്റ്റിമം ട്രാൻസ്പോർട്ടേഷൻ. ഓക്കെ, ഏറ്റവും ബെസ്റ്റ് ആയിട്ട് എത്ര കയറ്റാൻ പറ്റും. അപ്പോൾ അവിടെ 0-1 പ്രോഗ്രാമിംഗ് ആയിരിക്കും. ഓക്കെ, ഫസ്റ്റ് കണ്ടെയ്നർ ലോഡ് ചെയ്യണോ വേണ്ടേ, യെസ് ഓർ നോ. ഓക്കെ, യെസ് ഓർ നോ, യെസ് ഓർ നോ, അങ്ങനെ. So number of decision variables is equal to number of containers in that പോർട്ടലുള്ള കണ്ടെയ്നേഴ്സ് ആയിരിക്കും. അപ്പോൾ ഏതൊക്കെ ഡിസിഷൻ വേരിയബിൾസ് ആണ് 1 ആണ്, അത് നമ്മൾ ലോഡ് ചെയ്യും. ദാറ്റ് ഈസ് ഫോർ ഒപ്റ്റിമം ട്രാൻസ്പോർട്ടേഷൻ, ഫോർ ഒപ്റ്റിമം പ്രോഫിറ്റ്. ഓക്കെ, അപ്പോൾ അങ്ങനെയുള്ള സിറ്റുവേഷനിലെല്ലാം 0-1 ഇൻറ്റിജർ പ്രോഗ്രാമിംഗ് ആണ് യൂസ് ചെയ്യുന്നത്. നൗ വി ആർ ഗോയിങ് ടു ഡിസ്കസ് ദ ഫസ്റ്റ് വൺ, integer linear programming problem. Okay, that means all the decision variables should be integers. And അതിനു വേണ്ടി പല പല മെത്തേഡ്സ് ഉണ്ട്. വി ആർ ഗോയിങ് ടു ഡിസ്കസ് എ മെത്തേഡ് ദാറ്റ് ഈസ് കോൾഡ് കട്ടിംഗ് പ്ലെയിൻ മെത്തേഡ്. ഓക്കെ, സോ കട്ടിംഗ് പ്ലെയിൻ മെത്തേഡ് ഈസ് ഫസ്റ്റ് വി അപ്ലൈ ദ സിംപ്ലെക്സ് മെത്തേഡ് ടു ഗിവൺ LPP. ഓക്കെ, തന്നേക്കണ LPPയിൽ ഫസ്റ്റ് ഓഫ് ഓൾ വി ആർ ഗോയിങ് ടു അപ്ലൈ ദ സിംപ്ലെക്സ് മെത്തേഡ്. Our aim is to find an integer solution, an optimum integer solution. Okay, in the optimal solution, if at least one decision variable is not an integer, then we can apply the cutting plane method. Because if all the decision variables are integers, then that is the optimum integer solution. Okay, if at least one decision variable is not an integer in the optimal table, then we have to apply the cutting plane method. Okay, so in this cutting plane algorithm, we introduce a new constraint. New constraints, they are called Gomory's cutting plane. Okay, they are called Gomory's cutting planes. So if at least one of the decision variable is not an integer, then we have to introduce an extra constraints. They are called Gomory's cutting planes, one by one. കാരണം ആദ്യം നമ്മൾ ഒരു കട്ടിംഗ് പ്ലെയിൻ ഇൻട്രൊഡ്യൂസ് ചെയ്യും, എന്നിട്ട് അത് വെച്ച് ഒന്നുകൂടി ഒപ്റ്റിമൈസ് ചെയ്യും. If all the decision variables are again integers, then we can stop there. Otherwise, we have to introduce one more cutting plane. Okay, that's why it is one by one. The new constraints successively reduce the feasible region until an integer optimal solution is found. Okay, the algorithm is like this. Suppose suppose this is our suppose uh, this is our feasible region. We assume that this is our feasible, a convex region, feasible region, and also we assume that suppose this is our optimal solution. Suppose this is optimal solution of original LPP, not integer LPP, normal LPP. Okay, so maybe the solution is x1 equal to some 3 by 2 and x2 equal to some 7. Okay, suppose we have only two decision variables. So in this case, our aim is to we are going to find an optimum integer solution. Okay, but for normal LPP, this is the optimum solution. But here x1 is not an integer. Okay, x2 is an integer, but x1 is not an integer. Okay, so we have to find new solution, new integer solution. Okay, so what is our algorithm? Algorithm ചെയ്യുന്നതാണ് by introducing the new constraints successively, it reduces the feasible region until an optimum solution found. That means we are going to introduce a new solution, new constraint. Now ഒരു constraint നമ്മൾ extra introduce ചെയ്യും. Okay, and we throw out this side. Okay, under the guarantee that this side doesn't contain any integer solution. ഈ സൈഡിൽ വേറെ ഇൻറ്റീരിയർ സൊല്യൂഷൻ ഒന്നും ഇല്ല എന്നുള്ള ഉറപ്പ് കിട്ടുന്ന രീതിയിൽ we introduce a constraint. Okay, so what happened? So now new feasible region is like this. Okay, then we are going to solve our optimum problem, our given problem in this new solution region. Okay, എന്നിട്ട് കിട്ടിയ optimal solution again integer solution ആണെങ്കിൽ okay, otherwise again we introduce a new constraint, that is called cutting plane. Cutting plane means we remove some part of the feasible region such a way that such a guarantee that it doesn't contain any integer solution. Okay, integer solution ഇല്ല എന്നുള്ള ഉറപ്പുള്ള രീതിയിൽ നമ്മൾ ഒരു പോർഷൻ നമ്മൾ കട്ട് ചെയ്ത് കളയും. ഓക്കെ, അതെങ്ങനെയാണെന്നുള്ളത് ജസ്റ്റ് തിയറി ഒന്ന് പറഞ്ഞു പോവാം. തിയറി അത്ര ഇമ്പോർട്ടൻ്റ് ആയിട്ട് നിങ്ങൾക്ക് വേണമെന്നില്ല, പക്ഷെ എന്തായാലും ജസ്റ്റ് ഒന്ന് ബ്രീഫ് ചെയ്ത് നിങ്ങൾ പോവാം. Okay, for example, we consider a problem maximize z is equal to 2x1 plus 10x2 plus x3 subject to the constraints, these constraints, yeah, where x1 x2 x3 are positive integers. Got it? Here the variables are non-negative. Not only non-negative, they must be integers. Such problems are called integer linear programming problem. So this is a ILP, integer linear programming problem. Okay, so this is a normal LPP with the extra one condition, the decision variable should be an integer. Okay, how to solve this problem? The algorithm, the method is, first we have to solve this problem using our usual simplex method. Okay, you can use any of the simplex method for solving this problem. So first we are going to find the solution of this simplex problem using simplex method. So actually we have already discussed this problem, example 6 of our simplex method. Using simplex method we can solve this problem. So this is the optimum table of that simplex method. Okay, അപ്പോൾ ഇതിനെ നമ്മൾ സിംപ്ലക്സ് മെത്തേഡ് ഉപയോഗിച്ച് സോൾവ് ചെയ്യുക. So this is our optimum table. Then here all the cj minus zj's are less than or equal to 0, so optimum is reached, and optimum solution is from this optimum table. Here the value of x1, what is x1? Here x1 and x3 are non-basic, isn't it? Here x2 s2 s3 are basic, and so x1 and x3 are non-basic, they are outside. Okay, that's why x1 equal to 0 and x3 equal to 0, and the value of x2 is nothing, it is 15 by 2. The value of x2 is 15 by 2. So this is the optimum solution of this LPP, normal LPP. There is no, suppose normal LPP means, what is normal LPP? Instead of this condition we assume that x1 x2 x3 is only greater than or equal to 0. Okay, so this is our normal LPP, usual LPP, without any integer restriction. Only assumption is x1 x2 x3 are non-negative. Under this this problem, the solution of this problem is like this. This is the solution of this problem. Here but here it is clear that the decision variable x2 is not an integer. X1 is integer, x3 is also integer, but x2 is not an integer. Okay, so this is the situation. So this is an optimum solution of normal LP, but this is not an optimum solution for integer LPP, because in the case of integer LPP, all the variables should be an integer. Okay, so how to solve it? So here the decision variable x2 is not an integer. Then so we are going to introduce a Gomory's constraint. Gomory's constraint means it is nothing. Gomory's constraint means what? Suppose this is the present optimal solution, then we are going to introduce an extra constraint such a way that it removes a part of the visible solution. Such a guarantee that this part doesn't contain any integer solution. മനസ്സിലായ ഈ സൈഡിൽ വേറെ ഇൻറ്റിജർ സൊല്യൂഷൻ ഒന്നും ഇല്ല എന്നുള്ള ഉറപ്പിന്മേൽ നമ്മൾ അത് സ്ഥലം കട്ട് ചെയ്ത് കളയും, എന്നിട്ട് പുതിയ പുതിയ റേഞ്ചിൽ നമ്മൾ സോൾവ് ചെയ്യും. ഓക്കെ, ദാറ്റ്സ് ഐഡിയ ഓഫ് Gomory's constraint. So first we are going to introduce Gomory's constraint. So how to introduce Gomory's constraint? So this is algorithm. Choose a basic variable xk having highest fractional value. Choose a basic variable xk having highest fractional value. In case of tie, you can choose any one of them. Suppose the equation corresponding to xk is like this. ഇതാണെന്ന് വിചാരിക്കുക. For example, in this example, consider this example. Okay, in this example, here the fractional part is 1/2, isn't it? Actually here 15/2 is equal to 7 plus 1/2. Okay, and this is a basic variable with a fractional value. Fractional value means it is 7 plus 1/2. Okay, so suppose it contains more than one basic variable, then we have to choose one basic variable with the highest fractional value. That's all. So നമ്മൾ അത് choose ചെയ്തു. Then we can write the equation corresponding to this basic variable. How to write the equation? The equation is nothing. 5/2 x1 plus 1 x2 plus 1/2 x3 plus 1/2 s1 equal to 15/2. Okay, so that's the idea. So corresponding to this highest corresponding to the basic variable xk having highest fractional value, we can write the equation sigma I is equal to 1 to n ai xi equal to b. Okay, in this previous example our basic variable is x2, and what about b? In the previous example b is nothing, b is 15/2. b, the present value of our basic variable, that is 15/2. Okay, how to form this equation? This is very easy. This equation is this one. 5/2 x1 plus 1 x2 plus 1/2 x3 plus 1/2 s1 equal to 15/2. That is the equation corresponding to the basic variable x2. Okay, once you write the equation, then next step is we have to factorize all these coefficients such a way that integer plus something. Here this is called the floor function. Floor function means an integer less than or equal to the given number. Okay, the highest integer which is less than or equal to given integer, that is floor function. Okay, so floor function means highest integer which is less than or equal to given number, so that is a floor function. So we can write every number as like this, floor of that number plus something. Okay, similarly we can factorize this b as like this, floor of b plus something. So what about this something? Something is always positive and in between 0 and 1, isn't it? So these fractions are always 0, less than or equal to, less than 1. All these fi's are like this, 0 less than or equal to, fi less than or equal to 1, depending on the number ai. If ai is an integer, then corresponding fi is 0. Okay, if ai is a non-integer, then fi is a value in between 0 and 1. You got it? So all the fi's are in between 0 and 1. And what about this fraction value f? F is like this, 0 less than f less than 1, because now we choose a basic variable with the highest fraction value. So guarantee is that b is not an integer. That is a guarantee, b is not an integer. We choose xk such a way that highest fractional value. So the present solution of xk is b, and we know that b is not an integer. That's why we're using Gomory's cutting plane method. So b has a positive fraction. So we can write b as integer function plus in some floor of b plus f. In the case of x2, in the last example, our b is equal to 15 by 2. So we can write this b as floor b plus fraction. So what is floor b? Floor b is 7. 7 plus 1 by 2. So here this is our floor b, this is our f. You got it? So f is always in between 0 and 1, but all the fi's are in between 0 and 1, but in time maybe fi may be 0. That depends on ai. Okay. So this is the idea. So we have to split the given equation as like this. Then a simple rearrangement. We rearrange like this. B part na left leg and this take the sigma fi xi to the right hand side. So this equation like this: sigma floor ai xi minus floor b is equal to f minus sigma fi xi. Okay, e portion e side leg pova, e portion e side leg edukka. That's all. Okay. So what happened? Okay, so here all the floor AIs are integers. Okay, here all these AIs are integers, and all these and here all these AIs and all the floor functions are integers. Okay, so if x equal to x1, x2, xn belongs to a feasible integer solution, suppose okay, what is our algorithm? Our algorithm is like this. We have a feasible region for non-integer LPP, and this is the optimal solution, and this optimal solution is not an integer solution. So we have to remove a portion of this solution. We have to remove a portion of this feasible solution such a way that it doesn't contain any integer solution. That's our A. Okay, so if x equal to x1, x2, xn belongs to feasible integer solution, that means suppose we consider a solution. Okay, we are interested only on integer solutions. All the x's are integers. Okay, suppose this is a integer solution belongs to the feasible region. This is an integer solution belongs to the feasible region. Okay, suppose this is all right. Suppose this is a feasible integer solution. Okay, ഇതാണ് feasible integer solution നിങ്ങൾ വിചാരിക്കുക. Then what happened? Then suppose this x is a feasible integer solution. Then what about this left hand side for this integer solution? Okay, നമുക്ക് integer solution ഇല്ലാത്ത ഒരു സ്ഥലമാണ് റിമൂവ് ചെയ്യേണ്ടത്. സോ നമ്മൾ integer solution ഉള്ള ഒരു സ്ഥലം നമ്മൾ assume ചെയ്യാം. Suppose x is an integer solution. If x is an integer solution, then what about this left hand side? This is an integer, isn't it? Okay, നമുക്ക് integer solution ഇല്ലാത്ത ഒരു പോർഷൻ റിമൂവ് ചെയ്ത് കളയണം. അതാണ് നമ്മുടെ ഉദ്ദേശം. So we assume that x is an integer solution. അപ്പോൾ അത് ഇപ്പുറ സൈഡിലേക്ക് കിടക്കണം അല്ലേ? x is an integer solution ഇപ്പുറ സൈഡിലേക്ക് കിടക്കണം. So if x is an integer solution, then this side is an integer. Okay, so RHS also an integer. Clear? LHS integer ആണ്, RHS integer ആയിരിക്കണം, because they are equal. And what about this f? F is in between 0 and 1. F is in between 0 and 1. And what about this quantity? Here xi's are integers, fi's are positive. We know that 0 less than or equal to fi less than or equal to 1, and 0 less than f less than 1, and all the xi's are integers. Okay, all the xi's are integers. That's our assumption. Okay, now we assume that all the xi's are integers. Okay, then what happened? LHS is an integer, RHS is also an integer, and this is a positive quantity in between 0 and 1. This is a positive quantity in between 0 and 1. So a positive quantity in between 0 and 1 minus a positive quantity is an integer. Okay, ശ്രദ്ധിച്ച് മനസ്സിലാക്കുക. F is a fraction in between 0 and 1, in between 0 and 1. Okay, so f is a fraction in between 0 and 1 minus a positive quantity. This is a positive number because all the fi's are positive. So a quantity in between 0 and 1 minus a positive quantity, and this whole thing is an integer because LHS is an integer. So what is the value of that integer? That integer should be less than or equal to 0. You got it? So this is our 0, this is our 1, f is somewhere here, f is somewhere here. So f minus a positive number, f minus a positive number, and this entire quantity should be an integer. That means this quantity belongs to here. It is less than or equal to 0. Okay, so therefore RHS is less than or equal to 0. You got the idea? അപ്പോൾ ഒരു ഇൻറ്റിജർ സൊല്യൂഷൻ എടുത്തിട്ടുണ്ടെങ്കിൽ ഇഫ് എക്സ് ഇസ് ആൻ ഇൻറ്റിജർ സൊല്യൂഷൻ ദെൻ the RHS value is less than or equal to 0. Integer ആണെങ്കിൽ, if this is an integer solution, then RHS is always less than or equal to 0. Okay, so what is the meaning? Okay, so okay, f minus sigma I is equal to 1 to n fi xi, it should be less than or equal to 0 if we consider an integer solution. Okay, so f minus sigma is equal to 1 to n fi xi is less than or equal to 0. The present solution does not satisfy 1. Okay, present solution എന്തായാലും ഇത് സാറ്റിസ്ഫൈ ഇല്ല. Why? The present solution means for the case of basic variables fi's are 0. Okay, the optimal solution doesn't satisfy this one because for the basic variables its fractions are 0, and for non-basic variables xi's are 0. Okay, so the optimum integer solution doesn't satisfy this fraction. You got it? Doesn't satisfy this inequality. Why? For the optimum integer solution, all the fi's are 0 because integer solution ആണെങ്കിൽ അതിൻ്റെ oh sorry, one second. Yeah, their fi's are the fraction corresponding to these numbers. So yeah, for the present optimal solution, this fi's are 0 for basic variables and xi is equal to 0 for non-basic variable. So what happened? So this sum is 0. For basic variables fi's are 0, for non-basic variables xi's are 0. So this sum is 0 for present optimal solution, and f is positive, so f minus this is a positive quantity. That means our present optimum solution doesn't satisfy this inequality. Okay, present optimal solution doesn't satisfy this inequality. Okay, so that means, so this is the situation, and this is our present optimal solution. And we introduce a new constraints like this: f minus sigma fi xi less than or equal to 0. Suppose this is the, so now we guaranteed that this constraint satisfies this equation. Okay, this equation, and this is the region corresponding to this equation, and again we confirm that our present optimal solution means that non-integer solution, the non-integer solution doesn't satisfy this inequality. Okay, that means by introducing this inequation, we remove this portion, we remove this part of the original feasible solution. Okay, so that is the idea of cutting plane method. So next, so for the present optimal solution does not satisfy 1 because all the fi's are 0 for basic and xi equal to 0 for non-basic, and f is positive. So LHS is a positive quantity. That's why we say that present optimal solution doesn't satisfy this inequality. Okay, so present optimal solution belongs to other side of the constraint one. So one is a cut. After introducing a slack variable g1, the Gomory cutting plane can be written like this. Okay, so next we are going to introduce this extra constraints to our constraint system. Okay, already we have some constraints. We introduce this constraint, this constraint for solving new LPP. Okay, and this constraint is called Gomory's cutting plane. Then how to create the Gomory's cutting plane? By introducing a slack variable. Okay, so this is the standard form, minus sigma fi plus, we introduce a slack where we can write this like this, minus sigma fi less than or equal to minus f. Then we introduce a slack variable, so minus sigma I is equal to 1 to n fi plus g1 is equal to minus f. Okay, and this plane is called Gomory's cutting plane. Generally this is a plane, hyperplane. In in whatever be the dimension, they are called hyperplanes. Okay, so that's why this is called a Gomory's cutting plane. So Gomory's cutting plane remove a part of the feasible region which contains no integer solution. That is a guarantee. Gomory's cutting plane remove a part of the feasible region which contains no integer solutions. Okay, so actually this constraint is like this. Suppose this is the equation of this constraint, then it's less than or equal to 0 means this side. Okay, and we have guaranteed that our present optimal solution doesn't satisfy this inequation. That means this, by introducing this constraint, it removes a portion of the original feasible solution. Then we apply our dual simplex method for solving this new LPP. So new LPP means this is the feasible region of new LPP. You got it. This is the feasible region of new LPP. So again we are going to search the optimal solution in the new region. Okay, using dual simplex method, because here the right hand side is negative. Right hand side is negative and all the constraints are less than or equal to type. So we are going to use dual simplex method. Okay, in the case of decision variable, okay. So in the last example, x2 has fractional value. So the equation corresponding to x2 is like this: 5 by 2 x1 plus x2 plus 1 by 2 x3 plus 1 by 2 s1 equal 15 by 2. Okay, you can write the equation corresponding to x2, that is 5 by 2 x1 plus 1 x2 plus 1 by 2 x3 plus 1 by 2 s1 equal to 15 by 2. Okay, then we have to split in such a way that an integer plus fraction like that. So this become 2 plus 1 by 2. This is 1 plus 0, no change. This is 1 by 0 plus 1 by 2, and this is 0 plus 1 by 2 equal to 7 plus 1 by 2. So what is our f1? So this is f1. Okay, f1 is 1 by 2. What is f2? f2 equal to 0. This is f3. This is f4 like that. Okay, this is our f. F is 1 by 2. F is always in between 0 and 1. Then how to introduce Gomory's constraint? Gomory's constraint is like this. Yeah, this is the Gomory's constraint. This is the Gomory's constraint. Minus sigma I is equal to 1 to n fi plus g1 equal to minus f. This is the Gomory's constraint. This you by heart ഓർത്തിരിക്കണം. How to introduce this Gomory's constraint എന്നുള്ളത്. So okay, so this is corresponding to, one second, yes, first we are going to write this equation, then we can write this Gomory's constraint. So what about this equation? F minus sigma fi xi. So this become, yes, here Gomory's constraint is 1 by 2. This is that 1 by 2. F minus sigma fi xi less than 0. This is Gomory's constraint. Okay, So here f is 1 by 2 minus 1 by 2 x1 minus, here the fraction is 0, so there is nothing corresponding to x2, and minus 1 by 2 x3 minus 1 by 2 s1, this is corresponding to s1, is less than or equal to 0. So this is called Gomory's constraint. This removes a part of the optimum solution such a way that it doesn't contain any integer optimum solution. Okay, so what is the cutting plane? The cutting plane is nothing. This is cutting plane is minus sigma fi xi plus a slack variable g1 is equal to minus f. This is the cutting plane. So the cutting plane corresponding to this is minus fi xi. So minus fi xi means this portion plus a slack variable, it is denoted by g1, is equal to minus f, that is 1 by 2. So this is the cutting plane. Okay, so next we plug in this constraint to our LPP, then again we optimize the table. Okay, so add this Gomory's constraint to the optimal simplex table, then find a new optimal solution by using dual simplex method. Repeat the same procedure until all the decision variables are integers or no feasible integer solution. Okay, next we are going to optimize the new LPP using dual simplex method, because this constraint is less than or equal to type, but RHS is negative. Okay, here this constraint is less than or equal to type, but its right hand side is negative. Okay, because minus sigma fi xi less than or equal to minus f. So here it is less than or equal to type, but right hand side is negative. Okay, ഈ value ഇപ്പുറത്തേക്ക് വരും. So less than or equal to minus f now. So this is a less than or equal type, but right hand side is negative. So we can't use our simplex method. So we will use dual simplex method. So this is the new table by introducing an extra constraint, that is Gomory's cutting plane. So here 0, its cost is 0, and g1 minus half, minus half, 0, minus half, minus half, 0, 0, 0. Okay, next we have to calculate zj minus zj. Next we use our dual simplex method, that's all. Okay, so what is cj minus zj? This is minus 23, 0, minus 4, 5. Okay, cj minus zj compute ചെയ്യുക, 0 minus 4, then dual simplex method നമ്മൾ എന്താ ചെയ്യുന്നത്? We choose an living element. How to find the living element? Now g1 is basic. Okay, we have to choose the maximum with the negative value. So here g1 is the living variable. Okay, ഇവിടെ എക്സ് ബിയിൽ നെഗറ്റീവായിട്ട് വന്ന ഒരാളല്ലേ ഉള്ളൂ, ദാറ്റ് ഇസ് മൈനസ് ഹാഫ്. Then how to find the entering variable? By taking the ratio. Okay, so we consider ratio with this row. So minus 23 by minus half, that is 46, minus 4 by minus 1 by 2, that is 8, minus 5 by minus 1 by 2 is 10, like that. Okay, ഇതിനെ നമ്മൾ ജസ്റ്റ് ഡ്യുവൽ സിംപ്ലക്സ് മെത്തേഡ് അപ്ലൈ ചെയ്യണമെന്നുള്ളൂ. Then what happened? Then we have to choose the minimum. So the minimum is corresponding to 8. Okay, minimum is corresponding to 8. ഇവിടെ നെഗറ്റീവിൽ ഏറ്റവും മിനിമം ആണ് നമ്മൾ ചൂസ് ചെയ്തേക്കണം കേട്ടോ. സോ ഇവിടെ ഓൺലി ഒരു നെഗറ്റീവ് ഉള്ളൂ, അതുകൊണ്ട് ഇത് തന്നെ വന്നു. സോ നൗ ദിസ് എലമെൻറ്റ് ഈസ് അവർ പിവട്ട് എലമെൻറ്റ്. ഇതാണ് നമ്മുടെ പിവട്ട് എലമെൻ്റ് ആയിട്ട് വരുന്നത്. ദെൻ ഇതിന് നമ്മൾ 1 ആക്കുക, ബാക്കിയെല്ലാം 0 ആക്കുക. സോ ദിസ് ഈസ് 1, then 0, 0, 0 യൂസിങ് കറസ്പോണ്ടിങ് റോ ഓപ്പറേഷൻസ്. ഇവിടെ എങ്ങനെ ഒരു ശരിയും, and here suppose this is r1, r2, r3, and if you take this as some r4, then now this value is 1. Okay, then what is the corresponding changes? What about r3? R3 goes to r3 minus, what is our r3? In r3 here it is 1 by 2. Okay, so what is the operation? R3 goes to r3 minus 1 by 2 r4. Okay, Similarly, what about R2? R2 goes to, this is 13 by 2. So R2 minus 13 by 2 R4. Similarly, this is 1 by 2. So R1 goes to R1 minus 1 by 2 R1. Okay. R1 goes to R1 minus 1 by 2 R1. Using these three operations, our table is like this. All these three elements are 0. These are the corresponding changes. Is it an optimal table? Yes. Here, yeah, Cj minus Zj's are all negative. Here, all the Cj minus Zj's are less than or equal to 0 and xb is positive. This is the condition for optimal solution in dual simplex method. Okay, so in dual simplex method, here all the Cj minus Zj's are less than or equal to 0 and xb is non-negative. So this is an optimal simplex table. Okay, then what is the solution corresponding to this optimum table? Here x2 equal to 7, x3 equal to 1, but x1 is now non-basic, so its value is 0. Okay, so the optimum solution is x1 is 0, x2 equal to 7, x3 equal to 1. This is the integer optimum solution and its maximum value is 71. Okay, so for integer restriction, this is the optimum solution 0, 7, 1. So the objective function value is corresponding value is 71. Okay. Now, integer restriction illegal solution. There is no integer restriction. Then what is the solution? Yeah, if there is no integer restriction, then solution is 0, 15 by 2, 0. The value is 75. And the geometry suppose this is the feasible region and we assume that this is the optimum solution. Suppose this 0, 15 by 2, 0 then, but this is an optimum, but this is not an integer solution. The value is 75, but this is not an integer solution. So we introduce a cutting plane that is called Gomory's cutting plane. Okay, in this case, what is our cutting plane? Our cutting plane is the equation. Yeah, in this example, this is the cutting plane. The minus x1 by 2 minus x3 by 2 minus s1 by 2 less than or equal to minus 1 by 2. So this is a plane, this is a hyperplane, and this plane means this plane throughout this portion. This means whenever we introduce extra constraint, our feasible region is this one, restricted out. That means we throw out this portion from our feasible region. Then we optimize the problem on this new feasible region. Okay, so we get another solution. We are searching the optimal solution on these vertices. Okay, vertex and on this vertex the new value table introduce after the first one iteration. Yeah, optimum value is 0, 7, 1. Okay, so this is an optimum integer solution with the maximum 71. That's cutting plane idea. Okay, so then there is a natural assumption. What about the round of solution? What is the round of solution corresponding to this optimum? Actually, our first optimum is 0, 15 by 2, 0. What is the round of solution? Here the round of solution is either 0, 7, 0 or 0, 8, 0, isn't it? These are the round of solutions because already these two are integers. And suppose we round area instead of 15 by 2, we use either 7 or 8. These are the two round of solutions. But they are not optimum. They are not optimum or they are not infeasible. ഒന്നുകിൽ ഇത് ഇൻഫീസിബിൾ ആയിരിക്കും, അതായത് ഈ ഫീസിബിൾ റീജിയൻ്റെ അകത്ത് ഉണ്ടാവത്തില്ല, അല്ലെങ്കിൽ they are not optimum because our optimum solution is 0, 7, 1. അപ്പോൾ നിങ്ങൾക്ക് ചെക്ക് ചെയ്ത് നോക്കാം കേട്ടോ. ഒന്നുകിൽ ഈ രണ്ട് സൊല്യൂഷൻസ് അവരുടെ നമ്മുടെ കൺസ്ട്രെയിൻ സാറ്റിസ്ഫൈ ചെയ്യില്ല, അതല്ല കൺസ്ട്രെയിൻ സാറ്റിസ്ഫൈ ചെയ്താൽ they are not optimum. You can verify it. So round of solution ഇതിലൊരു solution അല്ല, integer solution ഒരു solution അല്ല. What about the round of solutions? If x1 equal to 0, x2 is either 7 or 8, x3 equal to 0. അത് നിങ്ങൾ വെരിഫൈ ചെയ്ത് നോക്കുക. Either these two solutions are not feasible. Not feasible means they are not satisfy our constraints, given constraints, or they are not optimum. അതിൻ്റെ വാല്യൂ 71 താഴെയായിരിക്കും. ഓക്കെ, ഇപ്പോൾ ഇതിനകത്ത് ഇതിൻ്റെ തിയറി ഞാൻ ജസ്റ്റ് ഒന്ന് പറഞ്ഞെന്നുള്ളൂ, കാരണം എൻ്റെ ഒരു കൺസെപ്റ്റ് എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടെങ്കിൽ നോക്കാനായിട്ട്. മെയിനായിട്ട് നിങ്ങൾ ഇതിൻ്റെ